Welcome back to the deep dive.
Glad to be here.
So today we are wading into territory that honestly feels a bit like a cyberpunk novel,
Oh, yeah, absolutely.
but it is very much the reality of your local hospital right now. We are talking about artificial intelligence in medicine.
Specifically, radiology.
Right. The AI that reads your x-rays or your CT scans, your mammograms.
It's a field that has just exploded.
Yeah.
I mean, the promise is incredible, right?
Yeah.
You have these systems that can process thousands of images in the time it takes a human doctor to sip their coffee.
Just superhuman speed.
Exactly. Superhuman speed and accuracy that doesn't suffer from fatigue. Sounds like the silver bullet healthcare has been desperate for.
Ideally, yes. But we've got a stack of research here that suggests this silver bullet might have a bit of a wobble in its trajectory.
A significant wobble.
Yeah. We're looking at the hidden mechanics of AI today, and the big theme jumping out from all the literature is bias. But I want to pause there because when we say bias, I think most people picture a robot that's been programmed to be mean or prejudiced.
Right, and that is the first major misconception we need to clear up. We aren't talking about an algorithm having a personality or a political stance.
Which is good to know.
We're talking about bias in the statistical and engineering sense. It's much more slippery than just human prejudice. It's really about how math breaks down when it meets the messy reality of human biology.
So our mission for this deep dive is to trace the life cycle of a medical AI model. We're basing this on a really comprehensive article published in Radiographics.
It's a fantastic breakdown of the machine learning life cycle.
It really is. And we want to understand exactly where these errors come from. From the moment a researcher collects the very first pixel of data, all the way to the moment a doctor decides whether or not to rush a patient into surgery.
Because apparently errors can creep in at every single step of that journey.
They absolutely can. And to understand how, you have to understand that in this field, we're usually dealing with 3 different types of bias all happening at once.
Right, so you've got the one everyone knows, which is social or implicit bias. That's the human baggage. Are attitudes, stereotypes intentional or not?
That's the human element.
Exactly. But then you have cognitive bias. That's more about how our brains take shortcuts.
Like heuristics?
Yes, heuristics.
Yeah.
A radiologist might see a pattern they recognize and just stop looking for anything else. It's a systematic deviation from objective judgment. And then you have a third one, which is where the machines really struggle. Statistical bias.
Okay, let's unpack statistical bias, because this is the mathematical side. I saw a great visual analogy in the research that uses a target to explain this.
The archery target.
Yeah, like the classic bullseye analogy.
It's the best way to distinguish between being wrong and being biased. Imagine you're shooting arrows at a target. If your arrows are scattered all over the place...
Like one high, one low, one left?
Right. That is random error. You just aren't very precise.
But if I'm an Olympic archer and I put 10 arrows in a tight cluster, but they all land in the top right corner...
That is systematic error. That is bias. You are precise, meaning your shots are consistent, but you are consistently inaccurate. You're missing the truth by the exact same distance in the exact same direction every time.
And in medicine, being consistently wrong is actually more dangerous than being randomly wrong, isn't it?
Oh, without a doubt.
Because if the machine is random, you realize it's broken. If it's consistent, you trust it.
That is the real danger. If a model has systematic error, it's predictably wrong. Take breast cancer detection, for example.
Yeah.
There is a lot of data showing that if you train a model mostly on images from white patients, it learns the patterns of breast density associated with that demographic.
But breast density varies by race, doesn't it? Black patients often have higher breast density.
They do. And density is the camouflage for tumors on a mammogram. So if you take that white patient model, which has learned to look for tumors in less dense tissue, and apply it to a black patient, it's going to consistently miss findings.
It's hitting that top right corner of the target over and over again.
Exactly. It thinks it's doing a great job, but it's looking for the wrong signal entirely.
So that really sets the stakes for you as the listener. This isn't just about fairness in an abstract sense. It's about whether the machine actually works for the patient sitting in front of it.
Precisely.
So let's go to the beginning of the assembly line. Phase 1, data handling. The ingredients. Now, I always assume that when an AI looks at an X-ray, it's just looking at the picture, the pixels.
You would think so.
Yeah.
But medical images are never just pictures. They're files usually in a format called DCOM. And those files are packed with metadata.
Like tags attached to the image?
Right. Tags that tell you the patient's age, their sex, the hospital name, even the machine settings.
It's like the EXIF data on a photo you take with your smartphone. Location, time, date.
Exactly like that. And the AI sees all of it. Here's the trap, though. If that metadata is messy,
Say the age is inputted wrong or the sex is swapped.
the AI learns wrong associations. Let's say you're building a model to find osteoporosis, which is low bone density. The model looks at the bone in the image, but it also peeks at the age tag.
Because older people are more likely to have osteoporosis. It's a cheat sheet.
It is a cheat sheet.
Hmm.
But if your training data has errors, if you have a bunch of 20-year-olds accidentally labeled as 80-year-olds, the AI might learn that healthy, dense bone equals 80 years old.
It builds a mathematical rule based on garbage data.
Garbage in, garbage out.
But here is the part of the research that really freaked me out. Even if you scrub that metadata, even if you delete the tags for age and race entirely, the AI can still figure it out.
Yes. This is known as the black box problem. There was a fascinating study where they showed AI models chest x-rays, just ribs and lungs, and they asked the AI to predict the patient's race.
Which a human doctor cannot do. You can't look at a grayscale skeleton and say this person is African American.
No, a human radiologist would just be guessing. But the AI guessed correctly with incredibly high accuracy. It was picking up on latent associations, microscopic differences in bone structure or tissue density that are completely invisible to the human eye.
Which sounds super impressive until you realize what it actually implies. If the AI can tell the patient is black, it can start using race as a shortcut for the diagnosis.
Exactly. If the data set shows that black patients statistically have higher rates of hypertension, the AI might stop looking at the heart and just look for the race pattern. It bumps up the probability of heart disease because of the patient's race, not because of what's actually happening in their chest.
It's profiling.
It is algorithmic profiling, and we don't know it's doing it because it's all happening inside that black box.
It's not just the machine making assumptions, it's the humans teaching it. We have to talk about data labeling and annotator bias, because for an AI to learn, a human has to draw a circle around the tumor and say, look here.
Right. And humans are notoriously bad at following instructions. There was a great example in the literature regarding nasogastric tubes, feeding tubes. You ask a group of annotators to mark the tube. Sounds simple, right?
You'd think so, but does tube mean the whole line, the tip, the entry point?
Exactly. One person marks the tip, another marks the side hole where the liquid comes out, another marks the whole length. If your instructions aren't crystal clear, or if you're outsourcing this to teams with different language proficiencies, you get label ambiguity.
So the AI gets confused. It's like trying to learn what a dog is, but people keep pointing at cats and squirrels too.
It creates a massive amount of noise. And then you have the issue of class imbalance. This is huge for rare diseases. Imagine you have a data set of 10,000 patients, but only 10 of them have a specific rare brain tumor.
Finding a needle in a haystack.
If you train an AI on that, the AI quickly learns a very efficient trick. Just say normal.
Yeah.
If it guesses normal every single time, it will be right 9,990 times.
That's a 99.9% accuracy rating.
It looks amazing on a brochure. But as a doctor, it's entirely useless because it missed every single tumor. It prioritized being right on average over finding the sick people.
Wow. Okay, this transitions us into phase 2, building the machine, or model development. And there's a term here that I absolutely love because it paints such a vivid picture. Frankenstein datasets.
It's a perfect descriptor. In the research world, getting high-quality medical data is incredibly hard. So researchers often stitch together multiple public datasets to get enough images. They take a head CT dataset from Boston, combine it with one from Stanford and another from the NIH.
Creating a monster.
Well, the real problem is data leakage. Suppose patient A went to a hospital in Boston, so their scan is in that dataset. But maybe they also got a second opinion at Stanford. Now patient A is in both datasets.
And if you use the Boston set to train the AI and the Stanford set to test the AI,
you have accidentally given the AI the answer key. It isn't learning to diagnose patient A, it is just remembering patient A. It's memorizing, not learning. So when patient B walks in someone it's never seen, the model fails completely.
it's like studying for a test by memorizing the order of the answers, A, C, B, D, instead of actually learning the math.
Exactly.
Yeah.
And another way we accidentally cheat is through improper feature engineering or imputation. Imputation happens when data is missing. Let's say you have a spreadsheet of patient data, but for 10% of the patients, the weight column is blank. You can't feed blanks into the model.
So the computer fills it in, usually with the average, right?
Right. It calculates the average weight of all the patients and plugs that into the holes. But if you calculate that average using all the data, including the data you're supposed to be testing on later, you've just leaked the global average into the training room. You've tainted the evidence.
It seems like there are a million ways to mess this up before you even turn the thing on. But let's say we survive that. We build the model, now we have to grade it. Phase 3, evaluation. You already mentioned the metric trap of accuracy. That 99% score, that actually means nothing, so what should we be looking at?
We need to look at the F1 score.
Okay, break that down for us.
So accuracy is just how many did I get right. F1 is a combination of precision and recall. It penalizes the model if it misses cases which are false negatives, and if it cries wolf too often, which are false positives. It forces the model to actually be good at finding the pathology, not just good at guessing the majority class.
And we also need to stop looking at just the one big number, right? We need subgroup analysis.
This is critical. You can have a model that works great overall. Let's say it works 99% of the time for men, but only 60% of the time for women. If your data set is mostly men, your average aggregate score might still look like a solid 90%.
But if you are a woman, that model is basically a coin toss.
Exactly. Unless you break the report card down and grade it separately for men, women, different races, different ages, you hide those failures in the average.
Okay, so we've graded the model. It passed. Now we move to phase 4, deployment. We are leaving the lab and entering the hospital. And this is where things get really messy, because the real world doesn't behave like a curated data set.
No, it doesn't. This introduces a concept called data distribution shift, or covariate shift.
To put this in perspective for the listener, this is like teaching a self-driving car to drive in sunny California. It's perfect. It knows what a stop sign looks like. Then you ship that car to Norway in the middle of a blizzard.
That's a perfect analogy. Technically, it's still driving. But the inputs, the light, the friction, the visibility have all shifted. The car panics. In radiology, this happens when a hospital simply upgrades their machines.
Just a software update.
Just an update. Maybe the new machine takes slightly sharper images. To a human doctor, it looks better. To the AI, which was trained on the old, grainy images, it looks like an alien landscape. There was a case cited in the literature where a hospital upgraded their mammography software, and the AI's recall rate, meaning the number of women it flagged for cancer, tripled overnight.
Tripled? That's a lot of terrified patients.
And a lot of unnecessary biopsies. All because the pixel values shifted slightly and the AI thought different meant cancer.
And this leads us to what is frankly the most terrifying part of this deep dive for me. The human element in the room. Automation bias. Because we assume that if the machine is wrong, the human doctor will catch it.
That is the assumption. But psychology tells us otherwise. Automation bias is the tendency to trust the machine over your own eyes. And we see two types of errors here. Omission errors where the AI misses a tumor, so the doctor assumes everything is fine and doesn't look closely.
And commission errors where the AI flags something that isn't there and the doctor agrees.
There is a scenario mentioned in the literature that really keeps me up at night. The code stroke.
Yeah, this one is heavy. Paint the picture for us.
So imagine the ER. It's 2 a.m. A patient comes in with slurred speech. You suspect a stroke. The protocol is time is brain. Every minute matters. You rush them to CT. The AI algorithm runs the scan and flashes a big red alert. Large vessel occlusion. A blockage.
And the treatment for that is serious.
Very serious. Powerful blood thinners or invasive mechanical surgery to pull the clot out. Now imagine you are a junior resident. You're tired. You're stressed. You look at the scan and you don't really see the blockage. But this million-dollar algorithm is screaming yes.
Do you have the guts to overrule it?
That's the question. And studies show that inexperienced radiologists are significantly more likely to follow the AI's incorrect advice. It's the experience gap. They assume the computer knows something they don't, so they administer the treatment.
And if the AI was wrong, if it was a false positive, you've just put a patient at risk of a major hemorrhage for no reason.
Exactly. That is automation bias in action. It literally turns off your critical thinking.
And this creates a vicious feedback loop, doesn't it? Because if the doctor agrees with the biased AI, they write a report saying, yes, there was a blockage.
And guess what the next generation of AI is trained on?
That exact report.
The snake eats its own tail. The bias gets baked into the medical record, which becomes the ground truth for the next model. And this is where we get into the deep social impact. We risk automating inequality.
The research makes a really interesting distinction here between inequity and inequality.
It's an important nuance. Inequality is just a difference, like an unequal distribution of resources. Inequity is an unjust, avoidable difference. It's unfairness. And AI can exacerbate this through underdiagnosis bias.
There is that famous case. A huge study regarding healthcare costs as a proxy.
This is the classic case study in AI ethics. There was an algorithm used by major health systems to predict which patients were high risk and needed extra care management. To predict sickness, The algorithm used healthcare costs as a proxy. The logic was sick people cost more money.
Which makes sense in a spreadsheet.
In a vacuum, yes.
Yeah.
But in the U.S. healthcare system, historically, less money is spent on black patients than white patients for the exact same level of illness. Access issues, insurance gaps, systemic bias.
So the AI saw that black patients cost less.
And assumed they were healthier. So a black patient had to be significantly sicker than a white patient to get the same risk score and get that extra help.
It denied them care because they had been denied care in the past.
Exactly. It took a historical injustice and codified it into a mathematical rule.
That is heavy. But we don't want to leave everyone completely hopeless. The field is aware of this, and there are solutions proposed in the literature. One of them sounds like a paradox. Equitable bias.
It does sound wrong, doesn't it? Usually you want to remove bias. But equitable bias means introducing intentional bias to balance the scales.
Fighting fire with fire.
Basically, it involves oversampling. If your data set is 90% white and 10% black, the model will largely ignore the black patients. So you intentionally duplicate the black patient data, or you actively recruit more participants to make the training set 50-50.
You bias the data distribution to force the model to pay attention to the minority.
Exactly. You have to distort the real-world proportions to get a fair and equitable result. And beyond that, the biggest solution is governance.
Humans in the loop?
But not just any humans, a multidisciplinary team. You need statisticians, clinicians, hospital admins, all watching the dashboard continuously. You can't just buy an AI, plug it in, and walk away.
It's not a toaster. It's more like a high-maintenance sports car. You have to constantly tune it.
You have to monitor for that covariate shift. You have to ask, is this model still working for our patients right now with our current machines? If you aren't auditing it, you aren't practicing safe medicine.
So bringing it all back home, we've gone from the pixels to the hospital floor. At every step, bias is a risk. The key takeaway here seems to be that AI is a tool, but it's a tool that can lie to you with extreme confidence.
That's it. It's not magic, it's math. And math is only as good as the numbers you feed it. For you as the listener, whether you're a patient, a techie, or a doctor, the best defense is skepticism.
Don't let automation bias turn off your brain.
If the AI sees something, verify it. If it misses something, trust your gut. We are nowhere near the point where we can take our hands off the wheel.
Now, before we sign off, we usually like to leave you with a provocative thought, something that is just over the horizon. And there is something happening right now with generative AI, things like ChatGPT and Midjourney, that is starting to bleed into this medical field.
This is the next frontier. We talked about how hard it is to get diverse data right. Well, researchers are starting to use generative AI to create synthetic data, basically using AI to draw fake X-rays of rare diseases to balance out those data sets.
So making up fake patient data to fix the class imbalance.
Yes, and on paper it works. But here is the nightmare scenario. We call it model collapse. If you train AI on AI-generated data and then train the next AI on that data, eventually the models detach from reality entirely.
Like a photocopy of a photocopy of a photocopy.
Exactly. The image degrades. The models might start converging on a weird, distorted average of what a human looks like. If we start treating synthetic diversity as real diversity, we might end up with medical models that are incredibly confident, perfectly balanced, and completely hallucinated.
We might be building a highly detailed map of a territory that doesn't actually exist.
That is the risk. And that's the frontier we need to watch out for next.
On that slightly terrifying note, thank you for taking this deep dive with us today. Keep asking questions, check your sources, and maybe don't trust the robot with your life just yet.
Stay curious.
We will see you next time.